everyone to Transformation Tuesday for the Arizona SciTech Festival. We're so excited to have you here today. We're just asking in the chat, where is everyone from? So let us know if you're a CSO, student, community member, and where you're located. I know CSO Simon, is up by the White Mountains as well. Destiny, Destiny's from the White Mountains and a snow day today.
Oh wow, what a difference from Arizona, like down in Phoenix, right?
I know, I've heard everybody else is under snow except for, just a couple of states. So we're lucky. So we have Cassie on today. She's actually one of our interns from the SciTech Institute. She's a high school student, so she was super excited to join today. Thanks, Cassie, for joining. CSO Valentina from Western Arizona. I think we have CSO Prisha maybe on as well, I think I saw. A couple of other CSOs on there, so if you just want to drop in the chat.
Pennsylvania.
Wonderful. Prisha's here in Arizona. Wonderful. Awesome. Well, I think, Chris, what do you think? Shall we go ahead and get started, and then we'll wait for Dave to join in after your presentation? I know we'll have some time for some questions, and then we can go from there.
Yeah, absolutely. Let's go ahead and do that. First, I just want to start off by saying, I know all of you are dealing with the same sort of situations where you're at home or you're in a different environment. So you might see my dog show up, and I apologize in advance if he barks or does anything like that. My daughter, she is in 8th grade. So even though she knows I'm on this video call, she tends to walk in sometimes. So you may see other people in the screen, and my apologies in advance. Hopefully things don't get too loud. But I do want us to have an open dialogue back and forth. I know Hope said we'll open up the chat and the line for questions and answers. So at any time, feel free to just drop in a question. I know we're all curious about the company, and wanted to share just a high level of what we do. But before we jump in there, I wanted to share something interesting. I think all of us have heard so many things about the pandemic, and depending on where we live in the world or our states, are facing some of the similar challenges. And one of the very interesting things is that companies like ours actually go into helping with the pandemic. So our chips are actually in ventilators, and our types of technology help keep the internet going. So the computers that we're on right now is all because of companies like ours. The same thing with making phone calls on your cell phones, texting your friends, things like that is all because of semiconductors. So our company is one of the types of companies that has been operating during the pandemic. And I kind of want to share some of the cool things that we're in, and some of the types of things we're doing. So feel free as I'm talking in the chat, tell me one of your favorite things you've done during the pandemic. If it's, FaceTime your friends, we're in those types of technologies. If it's working out and tracking your fitness, we're in a lot of those types of devices. If you have been playing video games with your friends, we're actually in a lot of video gaming consoles. So hopefully the pandemic has been made a little bit easier because of some of the technologies that our company makes. So let's move into what our company does. Let me see here. All right. From a high level, our vision and mission as an organization is to create semiconductors. So those little tiny chips I was talking about that power electronics to help make our world connected, more inclusive, and then obviously greener and safer. A lot of the things that our company does is help with energy efficiency. You might hear a little bit from some of our engineers or more technical experts like Dave and Al and so forth talk about some of those types of things. So feel free to ask them more detailed questions. One of the other things our company does is we're in various applications like power and analog and sensor and connectivity. What does that all mean? So I'll go through some examples in a little bit, but we're really focused on growing in specific markets. So you see there in the strategy piece, we're focused on automotive, industrial, cloud power, and IoT. A lot of folks wonder what IoT is. It's the Internet of Things, but there's so many different types of things that fall into IoT. And I'm actually close to one, so I'll spell it out because if I say the name, she will start talking to me. But Alexa is a device that is considered Internet of Things. So it creates that connected home. And if I say the name, she'll probably jump in and ask what I need. So we're not going to do that on, on this call. The other thing we're trying to do is create benchmarks and things like ethics, corporate social responsibility, and employee engagement. So a few of our team that's on the call, like Nahal and Jackie, they have been really instrumental in having our company grow in those areas. All right. So from a high level perspective, we're headquartered in Phoenix, Arizona, and I don't want to say here because a lot of you are located in different places. And we have around 34,000 employees around the world. Most of those employees communicate with us um, in things like video chats, like we're doing right now, or through computers or other types of communication than standard email because a lot of our employees are in manufacturing. So they're not sitting at a desk every single day. Uh, what we're focused on as a company, so if you look at that bar that's on your screen, our biggest area of content is in the automotive sector. And that's around 34-35% every quarter. Some of the things that we work on in automotive, and I always say if you pick a car, we probably have at least 10 parts in that car. Depending on the model and make, it could be more, but on average, I think it's been like 10 parts per car. So things like backup cameras, if any of your families have sensors on their cars where the trunks are to have like a keyless entry or open of doors and trunks and things like that, a semiconductor controls that. Power for windows, the infotainment system, so the radio, the whole dashboard, and a lot of them are fancier nowadays. They're coming out with great models every year. The backup cameras and the park assist. So a lot of those type of applications within the car come from our company. The other thing is LED lighting. I know now some of the cars have mood lighting, so you can actually pick which light you want in your car, whether it's like red or purple or green or blue, that you can actually pick what that looks like. The other thing outside of automotive, and here I talked about my dog, and he's actually jumping on my lap. Sit down. All right. Hi, Teddy. All right. So for industrial, medical, and aero defense, like aero defense sector, a lot of the things that we do there is energy infrastructure, the power conversion, the motor control, and sensors in that area. For communications, it's 5G infrastructure, US Type C solutions, so the connections for your electronic devices, and then also the way that your internet is transmitted. And then for the consumer sector, connectivity, power conversion, audio, video, imaging, and then in computing, there's several areas that we focus on as well. So let me walk you through a few of the products here and some of our recognition. So in the past year or so, I highlighted some of the major awards that our company has won or been recognized with. A lot of them are focused on corporate social responsibility, being a leader in our industry on some key areas like gender equality. You'll see that one in the middle at the top there. And then being a world's most ethical company. And at the time this presentation was made, we were a 5-time honoree, which is pretty unique because in our industry, there have been typically only a handful of companies recognized. Last year, there were, I think, 3 recognized, and we were one of those. And then Dave might talk a little bit about Strata that's in his organization, some of the things that his group is doing. And then we were named one of the fastest growing companies as well. Here's some fun statistics. I like to share some of the fun data so that hopefully keeps all of you engaged and paying attention. if you look at the far left of our screen, the adoption of LED drivers has reduced energy consumption and lighting up to 80%. Our advanced power conversion technologies increase efficiencies in server farms that result in over 30 million in power savings per year. Then if you look in the middle there, that's Al's area of expertise. So he might cover some of this. So here's the preview for Al. But every year, our company is recycling over 1,000 metric tons of scrap material from over 1,900, almost 2,000 pounds of precious metals. So every single semiconductor, in order for it to conduct for electricity, power, you need some sort of conduit. And it's typically like a copper or a gold. And Al will go through that a little bit. But when defective parts come in, we have to have a way to recycle those and hopefully reuse them. So they're processed, sorted, and either sold for reuse, or we determine what type of use we'll have with whatever is being recycled there. Then if you look on the far right, the supply chain output. So this number doesn't change very much year over year, and I didn't update some of these stats because our next annual report is about to be released and hasn't been released yet, but it's roughly around the same every year. In 2018, we shipped about 7 units per person in the world. So every single one of you has had something over the last year that you probably bought that has something of ours in it or something from the semiconductor industry. We ship over 37 billion products every 6 months. And if those products, those tiny little semiconductors were lined up part to part, they would circle the earth more than 2 times. Then if you look at this slide, the far left, we consume about 996 tons of copper per month. And 2% of a Boeing aircraft, for example, is made of copper. So in 1 month, we're using the equivalent of 221 large aircrafts worth of copper. And then in the middle there, you'll see our business continuity and resilience, which was a big part for 2020 during the pandemic. And obviously, that was very different than what we typically deal with since a pandemic is not a common occurrence. We navigate various disruptions every year and mitigate over 10,000 business continuity risks globally. So every day there's a potential to have 5.3 disruptions. So if you include that plus COVID, last year was a pretty busy year for us outside of just the pandemic. And then we work with key folks in our organization to make sure that we've got our right messaging going out to people and that we're all aligned at every single one of our sites. And then if you look on the far right, one of the other focus areas is greenhouse gas reduction. And those are some of our savings in greenhouse gases back in 2017. And like I said, over the course of the last few years, it's been about the same. I would guess that 2020 was a little bit different because there were less cars on the road due to so many people staying at home. All right. One of the reasons I asked where all of you are from was I kind of wanted to share a footprint of where all of our 34,000 employees are. And as you can see from this map, these are our major locations. They include our design and manufacturing facilities, design centers, and SECs. So the Solutions Engineering Centers is the group that reports into Dave Presack, who all of you will be hearing from. And then we have our manufacturing facilities as well. So if you take a look at this map, we're in all parts of the world. And one of the things that interested me to join the organization, I know from a STEM perspective, a lot of people look at engineering or math and the types of jobs they can get, but organizations and companies focused on technology aren't just for engineers or those that are majoring in more of a technical degree. It really interested me because my family immigrated here from Serbia, and I was born here, but all of my family lives overseas. And I was used to speaking in a different language growing up and dealing with various parts of the world. And when I moved to Arizona, I wanted to find a company that wasn't just based in Phoenix, where I could work with people all over the world. So I think it's really neat as you're going through school and kind of thinking about some of the types of things you want to do is who do you want to interact with on a daily basis? What does your job look like? I know for all of us, our job looks very different every single day, and I'm sure you'll hear that from everyone. But it's been a really, really exciting past 10 years, and I couldn't believe I've been at the company for 10 years. A decade sounds like a long time, but it's different every day because we're interacting with different people. Here is a little bit more about our manufacturing footprint. This is something that we shared with our financial community about a year and a half ago. And here it talks more about how many products are shipped. So if you think about that from a logistics standpoint, and I think a lot of you are familiar with Amazon shipping so many products and things, imagine shipping 72 billion tiny things to customers all around the world. There's a lot involved with those logistics. So if you look on the far left, that's our front end and substrate facilities. So that's where the beginning process happens for a semiconductor. So we start out with wafers, which are pulled in almost like a cone shape, and then they're sliced into tiny little, and I'm not in my office. I wish I could show you. I have one in my office to share. Maybe Al has one to show all of you later. But they're printed on a wafer in the manufacturing facilities, and that all starts at the front end. And oh, there it is. Thanks, Al. That's what a wafer looks like. So when they imprint on the wafer, it actually is like a blueprint or a map, similar to when you're buying a new, like your parents are buying a house and you see everything kind of sketched out on a piece of paper. That's what is happening to the semiconductor and the semiconductor process on the wafer. The actual blueprint for what the product will end up going into is actually etched in there and then cut and assembled and packaged. That happens in the back end portion. And then let's see what else. The third bullet point on there, it talks about the capacity and the difference in the wafers. And we purchased a facility about a year and a half ago, and we'll fully own it by 2022 here in the US, and that'll be our largest scale. The larger the wafer, the less waste you have and more cost effective it is to produce. So let's look at some of the major areas and mega trends that our company plays in. The first is automotive. And if you look at electric vehicles, a lot of the electric vehicles that you see out on the road have some sort of parts or components from our company, whether it's sensors or the power. I talked a little bit about being able to open your car from with keyless entry, or the trunks by waving your hand with the trunk with the key in your pocket. A lot of that is a technology that our company works on. For those of you that have seen in Phoenix in particular, they've done a lot of testing here. The rideshare services like Uber and Lyft, and they've had those things spinning at the top of their cars. That's a type of sensor that our company works with to kind of gauge what's around your vehicle as you're driving, and that will also help to create full autonomous driving, which we're a little bit a ways away, but we're moving in that direction. Then in the middle here, the industrial and cloud power. I talked a little bit about that. That's the connectivity portion for 5G infrastructure, for example, to be able to have quicker internet. If you're streaming, I know my daughter is in 8th grade, like I said, she likes to stream how-to videos on YouTube. It happens a lot quicker with the type of infrastructure and the setup of the city or town that you live in. And then for IoT, I know I mentioned Alexa. I have to make sure I don't say the name so she doesn't start talking to us. But those types of devices fall into the IoT, or just the connected. If you want to look at connected home, or a lot of our devices are connected to each other. I know there are some, I've heard washers and dryers, so white goods that are connected to your phone, and you can tell them when to start when you're not even at your house. You can have your lights turned on at a specific time, your garage door open from an app. That all plays into the IoT area there. All right, I'm going to move to solar power and clean energy. That's one of the things that our company is focused on as well. We've shipped enough power solutions capable of replacing 128 coal-powered industrial plants, which obviously has helped with pollution and cut down on those greenhouse gas emissions. And then talking a little bit about energy efficiency, some of you may have heard or seen some companies are testing out robots to pick products and bring them to conveyor belts to help ship products to customers. I've heard some airports in Asia actually are using robots for temperature checking of passengers. So a lot of those types of things require semiconductor to be able to move or do any sort of operation. So we could help US manufacturers save around 350 million per year by using some of our motor driven systems and facilities. So if you look on this slide here and just creatively think about what can happen if you have more efficiency in manufacturing, the conveyor belts and lifts that are all automated, and helping with energy efficiency overall with some of the things that we can install in the plants. Some of the really cool things that our company does is medical. And as I mentioned at the beginning, some of our parts go into ventilators, which is one of the reasons that semiconductors are deemed essential businesses. The other aspect of it is that whole connectivity. Without semiconductors, transportation systems are tied to how they operate based on the infrastructure that semiconductors help create, as well as just general connection, right? The way you're able to communicate and go to school now has been virtually over the computer. And a lot of that capability is based on some of our technologies. So if we look at the medical section, you can see that we're in implantable devices. They're on the top left. And then the bottom left, some clinical and consumer products. The top right, we're in hearing health, hearing aids, and then medical imaging as well. So here's an example of what can be done with some of our products when it comes to medical imaging and how much clearer the pictures are if you look at conventional, and then the far right with use of some of our products when they're incorporated in some of those medical technologies. So overall, our company looks to deliver an integrated manufacturing footprint and scale to drive an optimal cost structure, a very responsive supply chain with the amount of products that we're able to ship and deliver on time, become an innovator or a leader in power, analog, and sensor technologies to be able to keep up with the latest and greatest technologies that consumers like yourselves and our customers are looking to incorporate in their end product, and then building a portfolio that with applications that create complete solutions for our customers. So with that, that was my last slide. Hopefully that gave you something to be excited about as we lead into some of the other presentations. Let me go to the chat. I don't know if there are any questions or comments from the team.
So Chris, one of them says, do any of the medical technologies use particle acceleration?
I will phone a friend on that one. Dave, do you know the answer to that one? I know he's on. We might have to unmute him. I'm just reading some of your comments and smiling at them. The Mini Cooper lighting, yep, that's some of the things that we do. That is a lot of copper, very big supply chain challenge. And whenever I see Amazon vehicles and carts delivering things, I think about our massive supply chain behind the scenes. And there's Dave, if he wants to answer that question.
Well, I'd love to. I'm not actually sure. We don't work with that. It's more of the nuclear medicine where they start actually
Yep.
doing a lot of splitting genes and all that. We're mostly in more, I would call it domestic medicine, more about monitoring and looking for disease, looking at sensors of the body, making sure you're as healthy as you can be. More medical in that field.
Yeah, like I think one of the applications that I can think of is the pills with cameras in there that you can swallow and the doctors can see kind of what's going on in your body, uh, are some of the types of technologies we have. I thought for sure we're in everything, it seems like, so Dave would know the answer to that question. Let's see, did I miss something? Amazing technologies. Oh, my specific role. My job is corporate communication. So I'm on the same team with Dave. And one of the things that my department does, or I guess the types of things, is messaging to our employees. So employee communication, we deal with the press. So we have to make what Dave says sound like English to the average person because some of the stuff that comes from the engineers is super technical. And one of the things you'll enjoy from Dave is that he does a really good job of explaining technical things in a non-technical way. So that's part of what my team does is we have to kind of figure out what this all means and explain it to the press. We do speaking engagements. So whether it's speaking to students or externally to the company or industry, being able to explain what our company does. And then we work with the finance team to speak with our investors and shareholders. And then customers. So we work on customer communication. We did a lot of that last year during the pandemic response. And then what are some of the STEM careers we hire for? Definitely engineering. So a lot of our employees, regardless of their current role, whether it's more marketing focused, we even have some engineers in positions like HR. That's probably one of the highest hired STEM type of careers is engineering related. Otherwise, we hire all sorts of backgrounds. And I think based on what your passion is, you can fit into a company like ours and enjoy working in super technical areas. Let's see, specific type of engineering. Most of our engineers are electrical engineers. Double E's? No? What are you, Dave?
Well, I'm a double A, but most of the engineers here at Semi are material science engineers for manufacturing. We have double E's for doing designs. We have software engineers for doing advanced algorithm work. We have mechanical engineers that work in packaging, and we have chemical engineering to work in also the manufacturing. So many engineering roles here in the company.
All right, so all types of engineering. Maybe I worked with you too long, Dave, and I think everyone has a double E. I think our boss has a double E too. Maybe that's why I was thinking that. All right, any other questions? I think we've answered those that have come in so far. And like I said, my apologies again for the dog jumping on my lap, but that's our pandemic life. I pre-warned all of you, so hopefully you enjoy seeing a dog's face during the presentation. All right, if there are any other questions that come up and I'm not on the call any longer, feel free to send those to the organization. Hope can probably take all of those in, I presume, and then send them over to us, and we're happy to provide any follow-up. If you have questions about yourself or any tips that you'd like, we can definitely help there too. I think a lot of us have children either in your age range or that just moved up from the age range. I think Dave's are high school and college. So we're happy to provide any guiding tips if you want them other than your parents. I know my daughter likes to listen to everyone except for me, so.
Excellent. Thank you so much. This is Kelly Green from SciTech Institute. We just wanted to say thank you so much to On Semiconductor for putting this experience together today. We're so excited to have the students on the call. And I love that CSO Haley from Oregon had no idea that you exist in other locations.
I saw that.
So
thank you, everyone.
Thanks, Chris. I was just going to say, I think it's still Dave that's going to be going next. And then we'll do Al and then have Martin. present.
Okay.
Yeah, that's correct. We would love to have Dave go ahead and share next, and then we'll break into Dave giving us, or Al, excuse me, giving us a tour. So we're really excited. Chris, thank you so much for that overview. That was wonderful.
Oh my gosh, of course.
Learned a ton.
Of
It was
course.
awesome.
And I think there's a question that came up on what do high school students need to prepare now for an engineering role? And given that that was Dave's path, maybe he can start off with his and segue into answering that question.
That's fine, and I can just jump into that before I jump into my conversation. You gotta like math. There's a lot of math, 6 years of calculus, as a matter of fact. More and more tools are getting more automated, but as you get into the different sciences, put it this way, I started as an analytical chemical engineer and ended up as a double E. So you really have to, as you're exploring the different engineering sciences, you'll find one that you're really passionate about, and that's usually the one that's gonna drive you in the right direction. And again, once you know your passion, where you want to be to, then we can help you, or your college can help you kind of place you in what role would best suit your engineering desires. All right, so let me jump into here. All right, hopefully everyone can see that. Or working on it.
It looks great, Dave.
Yes. All right. So I have a very short time to talk about a very complicated subject. So we're going to do our best here. You've heard the word semiconductors about 20 times by now. Hopefully, by the time I finish, you at least understand what it is we're talking about. So just to start out, you in any given day have interacted with about 1,000 different semiconductors, right? If you've got headphones on, they're the ones making the noise in your ear. If you're looking at a screen, that's a semiconductor screen you're looking at. If you're communicating, those are semiconductors that are making the Wi-Fi possible. We control your washing machine. Semiconductors are used everywhere. Electric vehicles wouldn't move without semiconductors. Solar panels are semiconductors that connect to more semiconductors that convert it into power you can use. So robotics obviously wouldn't be anywhere without semiconductors for the sensing and the intelligence and all of that. And then, of course, they're used a lot in manufacturing. I love this picture. These are semiconductor products being used to manufacture semiconductor products. So you will see them everywhere, which gets kind of into what my career is. As the head of systems engineering, I have design centers around the world. Chris kind of mentioned that. They're in every continent. And what they work with are the customers that make all of the products you see in front of you. And what we try to do is use our technology to make their products better. So for the electric car, we want it to go longer. For solar energy, we want it to be more efficient. For your headphones, we want the sound to be clearer, right? So we work with companies that make all these products to try to make them better. So that's kind of what we do. And there's a good example of what we do. This is so much better in person, but we'll give this a whirl. This is, if you see the picture of the car, this is what the plug would plug into. This is called an onboard charger. This was designed out of our China group. This is what actually charges the electric vehicle's battery. This would be a game I was going to have if you were local to say, where is the semiconductor products? You see all kinds of colors and shapes. I wanted to show this for a couple of reasons. One is, that's heavy. One is it takes a lot of different products and technologies to solve these problems. The second thing is sometimes a semiconductor is the hardest thing to see in a circuit. They're actually the little black dots on this board. The big ones here, these are big capacitors. The big yellow ones here, these are transformers. These are all used to create this onboard charger. The semiconductor provides the brains and the brawn, if you will, for when to switch in these different technologies. But semiconductors themselves would not be able to do anything without all the supporting characters in this case. So that's why these engineers, they take their time, they build these very complex solutions using our products, but also many other products that are in the industry. So this is an onboard charger. Again, the little tiny dots are the semiconductors. I'll get into that in much more detail in a minute. But that is what my group does. Very proud of the group. They do everything from, like I said, audio projects to communications to chargers. So that's what I'm here for. So now we've used the word semiconductor about 60 times. So what is a semiconductor? Saw this comment and cracked me up. It's one of the hardest questions I always ask. I get asked, I say, well, you work for ON Semiconductor, what's a semiconductor? In this case, this is a quire semiconductor, or conductor cut in half, right? So what is a semiconductor? I'm going to reach through a very complicated device and explain what a semiconductor is. All right, everybody see it. It's a cord. All right, so this is a cord. This is probably you plugged in a million times into an outlet. It is composed of two items. One is the metal. There's copper wires running through here. These are steel ends here. This is what plugs into your wall. The metal is a conductor. It conducts electricity. So when you plug this in, power comes in, goes out the other end, transmits along the conductors, the copper wires in this case. So when you plug this in, why don't you get electrocuted? It's the plastic. The plastic is an insulator. The insulator blocks electricity. So in this one cord, you've got a conductor and an insulator. So you've got one that passes electricity, one that stops electricity. If you can imagine now, a semiconductor is in between these two states. You can make it conduct, you can make it block, or you can make it do anything in between. It's really important when we start crafting some of these solutions. A good way to look at it is for your headsets. How would you like it if it was either off or blaring loud, nothing in between, right? Sometimes you want it quiet. When you're listening to somebody, sometimes you want it loud, especially when you're in class. But imagine now if you only had one state, on or off. So you want to be able to control how you have things on or off, right? So that's where semiconductors come in. So when we start talking about semiconductor materials, you can't use metal. It's a conductor. Can't use plastic. It's a insulator. You need something that's going to give you both properties. So what is the most common semiconductor material? It is silicon. It is one of the most common elements on the planet, fortunately for us. And what is the most common material that has silicon in it? Those of us in Phoenix, this is a real easy answer. We live in the desert and are surrounded by it. If you guessed sand, you would be correct. So sand is comprised of silicon dioxide, right? This is one of the most common, but silicon dioxide can be found in everything, in water and plants, everywhere. You can get silicon everywhere. So we've got tons of sand. I know we're not tearing up beaches to get our silicon, right? But there is tons of silicon dioxide in the world. The problem is, we want silicon. Silicon is a great semiconductor material. So when we look at sand, we've got a dioxide problem. Right now, we need to remove the oxygen from sand, otherwise it's sand. So here's how we get to silicon materials that Chris was talking about earlier. So we take sand, silicon dioxide, we purify it and refine it. We do not want our chips to smell like the ocean. Just kidding. No, we want to do is make sure that any impurities that is not silicon dioxide, we want that removed. Anything like metals or organics, anything that would make it not pure silicon. So right now we take this, we purify it, and we refine it. Next, we heat the heck out of it. These are arc furnaces. They get these things super, super hot. And when you get them really, really hot, they actually will separate. Oxygen is removed, and what you're left with is silicon. Looks like something out of a Terminator movie. So this is pure silicon. So now we've removed the oxygen, we've taken sand, and we've made silicon. This is our base element. We now have a semiconductor material to work with. Are we done? Yeah, it's the right material, but it's unusable at this stage. So back to the ovens we go. We take the silicon, we put it into another crystal pulling furnace. So remember, this is not metal, this is crystal, very delicate structure. So we cook it and then we stretch it. We put it in a tube and we stretch this down the tube. And then Chris was talking about, right? We're talking about these ingots, what we're calling them. This is how you do that. You start with the silicon seed and you stretch it and you keep stretching it until it's about as big as it's going to get. And we cut those off and we call them ingots. There's our giant ones. There's also things called boules. They look like Hershey Kisses, but that's for other exotic materials. But this is the main way you'll see a silicon ingot created. And then once that is completed, it is sliced. And Al showed one before too, but I also have one here. Mine's smaller, his is bigger. But you also see just how thin these are sliced. So at this point, you have a very, very expensive mirror. That's about all it's good for at this point. But now you have a working material, you have a working surface to be able to start making semiconductor products. So all right, so now you've got this nice big flat surface area that's semiconductor material, right? That means it can be made into whatever you want it to made, and then we got to start with this. This is as technical as I'm going to get. It's going to go beyond me in a minute anyway. All right, so we take the silicon substrate, the nice flat piece that we just saw. Depending on, there's different chemicals you can add to it, in which case, if you see the red, you got arsenic, phosphorus, or antimony. That will give you what we call an N-type material. If you add boron, gallium, or aluminum, you get a P-type material. Think of the N-type as a giver. It wants to give you electrons. It gives everyone electrons. It's a giver. It loves to give everybody electrons. P-type, they're takers. They will take all the electrons you can give it. It doesn't want to give it back. So you've got these two different types of materials, and those become your building blocks. So now you can have, you've now doped, what we call doping. We've added these chemicals to the silicon, and we've changed a characteristic of the semiconductor. We can make it do things now. And so I look at it this way. These are the two most base elements that we use in almost everything we make. And you can tell by the color coding what material is used how. The first is the basic diode. These are the building blocks to make our integrated circuits. The diode, whoever came up with that symbol is a genius. It actually looks like a funnel. And that's exactly right. If you pour electric charge in the top, it goes out the bottom. That bar blocks it from going back the other direction. So it's like a one-way street. Energy goes one way, it can't come the other. This is really useful. So imagine your cell phone has got a battery in it. It's powering your screen. If this gets hit by lightning, the last thing you want is that energy coming back and blowing up your battery. So now you've got a diode that allows energy to go to your screen to power it, but also blocks unwanted energy that might come back and harm the battery. Diodes are very useful. You see them a lot. And they're on that project I showed you earlier. The next piece is the transistor, and this is the mighty transistor. This is what is the basic building block in almost everything modern you see. This is in memory, graphics cards, microcontrollers, everything. This is the transistor. So if you look just by the color coding, there's N-type connected to P-type, connecting to N-type. So we call this an NPN transistor. There's also PNP, right? So this transistor is a switch, but it's not just any switch, right? So if you put a battery on B, it connects C and E, and in this case, it's a light switch, the light would come on. If you remove the battery, C and E open up, the light would go off. But with this, the way we build these, it could be sometimes kind of on, sometimes kind of off. Or you can have different doping on it, that it only comes on if light is on it, maybe sound is on it, right? Or in solar energy, they turn on when solar energy is present, right? So we can now make a switch that turns on under different conditions and turns on in different ways. That is the basic building block for all modern semiconductors, right? So we make image sensors here. Those are a million little pixels, like you'd imagine, and each one is connected to a transistor that knows the difference between red and green and blue. So all these transistors are made very specifically for very specific functions. So these two elements between a diode and a transistor and then a bunch of different chemicals can be made into just about anything you want. And that disk I showed you before, it's incorrectly called a wafer at the start because it's just a disk. It becomes a wafer because you're adding layer after layer of design. So you can see the pattern on here now. This pattern are the different circuits. So these are all the different metal, all the different chemicals, all the different layers that make it into a circuit. So now it just doesn't conduct or not conduct, it does multiple things, right? One of these chips may be an audio amplifier that takes a microphone and gives you, your big voice, right? Some of these might just be diodes that protect your cell phone battery. All these different circuits are used for different ways. Once we have the magic formula, you pick it. Now, what also we don't talk about is there are many, many processes that are used. CMOS is one of the most common one, and that's mostly for like memory, graphics cards. All the big computing chips are made out of CMOS, but there's DMOS and trench and all these others that are used for big power applications or for big voltage applications. So there are many processes involved and many techniques involved to make these semiconductors. All right, so now you got these things down to these little squares. We've made them, we've built them up, they do what they're supposed to do, but they're still on that giant disk, right? So the next thing that happens is they're diced. So sometimes saws usually come in and they just cut it, slice it all up, like you see in the picture here, and they create the little dies. And then those dies are unusable because they're able to be connected to anything. So they're put in a package. They put these little wires, and they're ultrasonically welded, which means they vibrate really fast until they become so hot they weld. And you got these little wires that weld from the little die you made to this nice package. Now that package can be put on, could be attached wires to it, you can put it on boards, you can do all kinds of things now that it's packaged. Now these things come in all shapes and sizes. I've got some cases here to show you, but there's a reason why they come in all shapes and sizes. Good example, I've got two examples here. On the right here, you'll see the one with the car, and that says V-Track Dual. If you wanted to know how many transistors are in that package, this is massive. It's about the size of a deck of cards. There are 2 transistors in that package. The one below it is an image sensor. This is for a high resolution camera. It fits on the end of my pinky. It has millions of transistors in it. If you open up your laptop, please don't open up your laptop, but if you did, you would see a very large microprocessor in the middle, and it has billions of transistors in it. So what's the difference, right? Well, the one with the car is used to switch on and off the electric powertrain of an EV, electric vehicle. So massive voltage, massive power, you need big switches. Your image sensor, for example, is looking at microamps of current when it switches. So it can be very, very small on a very different process. So that's why we've got multiple processes, we've got all kinds of packages, we've got all kinds of techniques, because every one of these has a different function. The V-Track you see there, its sole function is to switch things on and off in an electric powertrain. The image sensor, all it does is it converts wavelengths of color that comes into it into electric signals, right? So those sound completely crazy different, but they're all done on semiconductor technologies with different processes and with different techniques. I know I'm moving a little fast here, but it's a big subject. So I'm looking at some of the packages. This is, let's see if we can see this. These are some of the bigger packages for, again, these are automotive or big motor applications that are switching very large signals. You've got smaller ones down here, but these are mostly for big power applications. And let's see how this shows up on camera. All right, so you can see all the different shapes here. Everything from very large to very small. And believe it or not, there are packages that I can't even show you. They'd actually fit 1 million of them in a salt shaker. So we got all kinds of packages for different reasons. The smaller ones you want for other, if we use packages like this, your cell phone would be your backpack, right? So you want to be able to make very, very miniature products for your audio, your video, for your cell phone, versus for something as big as a car, you need very big packages to switch big power and to be able to get heat out of that. All right, so this is the exact same slide Chris showed, but now we should have some context, right? So we manufacture both from the process, the front end is all about making these. So the front end is about, making silicon, growing silicon, making ingots, making wafers, doing all the etch. That's all front end and substrate. This is the substrate. The back end facilities is the one that slices it, dices it, and packages it. So between front end and back end, hopefully you now have a better understanding of what those mean. We do millions and billions of these units every year. When she said 150 millimeter and 200 millimeter, that's referring to the diameter of the ingots. So 6-inch ingots and 8-inch ingots we make in our factories. And then the back end, again, these are, once we dice these up and put them in packages, they actually package 1.4 or more billion units every week. So we make a ton of these parts because, again, they're used in pretty much everything that you interact with that has power. And that, I believe, is my time. So I'll open it up for any questions.
Dave, it looks like there's a lot of questions in the chat for you. So many questions. I was watching them all come in. I was like, wow, this is great. Would you like to go through those, or would you like me to ask them for you?
Oh, sure. I've just got I'm in present mode. I got to see if I get the chat. What the heck is chat? Sorry, I'm a WebEx person, so the Zoom thing.
No worries.
Oops.
So I can start while you're doing that.
All right.
Are there multiple types of semiconductors? And if so, around how many? You kind of touched a little bit about that, but if you want to.
Multiple types of semiconductors? Oh, there are pretty much every process has a very distinctive product it makes. If you're going to make a power product, you'll pick a process that allows you to do high voltages. When I talked about CMOS is the most used process for low voltage products like microprocessors and graphics chips and memories, that's because you can't put more than 5 volts on it, which does not do you any good in an electric vehicle that has an 800 volt battery. So you pick the process for the application. We mentioned LiDAR before. That is a light to electrical transistor. That's on a very different process than you would making a power device. So there are many, many, many different processes used, different materials, different doping techniques, depending on the application.
Great. And then the next one says, doesn't sand turn into liquid when it's placed in extreme heat and then it turns into glass? So when does it turn into silicone? Like at what temperature? Can you talk a little bit about that?
So if you take silicon dioxide and actually hit it with tons of heat, you will get glass. If you take it and heat it even farther, the actual oxygen breaks away from the molecular structure, leaving you with that metal-looking device, that silicon metal-looking clump. So yes, it would go sand, glass, silicon, but depending on the heat.
Awesome. And then the next one is, how long does it typically take to convert sand into pure form of silicon?
That's a good question. I do not know, and I don't know if Al can help me out on that one. I know it takes 6 months about from start to finish, but a lot of that is also putting all the layers and all the etchings and all of that and growing the crystal up. So I don't have that answer. Oh yeah, you're right. There's a ton of questions here.
I told you, yeah, there's so many in there.
Let me get to where my stuff starts. Yeah, 6 years
We're
ago.
at how long? Looks like we're at the Cassie asked, how long would you talk about 6 months? About 6 months, and how many steps does it take to make one semiconductor? And then you can work your way down on those questions.
Yeah, that's a very good question. So the steps it takes, that's why we call it a wafer, right? Each layer is another layer in the wafer. So it depends. Some of them, the more complicated they are, the more steps they are, the more simple they are. Like a diode could be just 1 or 2 layers, but you may get like a microprocessor that's switching at gigabits a second, right? That has many, many layers for the different layers that you've got to work with. So every one is different. Every every process is different, every method is different. It depends on the depth. So MOSFETs, which are the big switches for power, they're trench, which means you build these big towers, which means lots of layers, and they take longer. So it just depends, again, on the process. I've seen as many as 20 layers. I've seen as few as 3 to 4 layers. All right, what makes silicon a good conductor? Isn't it a mellow? So silicon, again, the real reason why it's a semiconductor is it is made, it passes valence electrons relatively easily when it's doped properly. So you can make it not move electrons freely. You can make it move freely. Keep in mind, when you put electricity on it or potential difference across it, you're going to get these movements in electrons. And so it does that very well. So when you're building your structures, you've got help by the potential difference across your wafer is actually creating these pipelines of electrons, if you will. So it can be a very, very good conductor. How did engineers figure out how to combine? Isn't that funny? It is a lot of chemical science. Because I've listed 3 that creates P-type. Each one of those has very distinctive characteristics. Some of them will give you more resistance, some of them will give you less resistance, but slower turn-on time. So you work with the different chemical components, you work with different processes. This is what I called material sciences earlier. That's why we have teams of engineers that work with the different materials, both chemicals, different conductors. We use titanium and gold and silver for conductive elements. We use all kinds of arsenic and other chemicals that, yes, we do experimentation all the time on how to get the best switch or the best sensor. So yes, it is a lot. I wouldn't say trial and error, but it is a lot of science. They look at how the covalent bonds at a molecular level, are they tight? Are they loose? Can they be pried apart with electricity, which is good for an insulator? Can you bind them tightly, which makes a good conductor? So there's a lot of science involved. And I bet you there's a little trial and error as well. You might be surprised in good or bad ways as you're experimenting with this. Bryce, who's 5, wants to know if you're an artist. What do I use the big board for? That's funny. I am known to be the worst artist on there. They call all of my drawings stick figures. But the big whiteboard is my big to-do list. I start every morning by putting everything I've got to do, and I fill it out. I do have this drawing. So I'm not the artist, but my daughter is, who made this one. This was about 20 years ago. So I do have art on the board, but it's not mine. Why are they wafer shaped? I see that they are diced. Why not rectangular shaped? All right, so it has to do with, again, that oven that actually pulls it down. And most materials, and there's waste, obviously, you're right. The perfect would be a rectangle. But how that's extracted through the circular to have even resistance around. If you make a square, you'll have more resistance in the corners than the flat. So you want it perfectly circular to get that even stretch as it comes down. So there are leftovers. We have scrap all the time, but we recycle as much as possible. We're actually one of the leading recycling semiconductor companies. What do you do? Yeah, there's that answer. That approximately what size are the largest and smallest semiconductors manufactured? So this is where I get semantics. We don't make semiconductors, we make integrated circuits. Largest and smallest, so the smallest I've seen are about 5 millimeters square. I can't even make my fingers that small. They're the width of a hair pretty much. They're very, very tiny. The largest semiconductors are some of the bigger switches, and they can be, I don't know, 2-inch square. They're very large. Again, those are for big power transfers. You see those for 1200 volt switches and stuff like that. Do the semiconductors have to be a certain distance from each other? Very good question. There is a certain thing when you get into high voltage, it's called arc distance. So in other words, if you're dealing with very high voltages, the electricity will jump from circuit to circuit, which is very bad. So yes, there are what we call, there's distances between both conductors and chips to make sure that we don't have any electrical arcing between those. Yeah. What are some types of impurities in a semiconductor? That's a very good point. I'm sure you have never heard of the term bunny suit. We have clean rooms in these manufacturing, and they're so clean that the air is scrubbed and scrubbed and scrubbed. And you have to put on what they call a bunny suit, which is a clean suit, which has no dust, no nothing on it. And you go into there. And even after all of that, if they show you how many parts per billion there are, you can see exactly when the torque came through, because no matter what you do, you're bringing in impurities into the system. And that could be dust, it could be dirt, it could be anything, right? That gets into that system when you're growing or during your layers, it causes problems. So yes, you're seeing more and more production being automated where they seal it all off to try to prevent that. But yes, impurities, you've got both from how well do you refine and purify the silicon dioxide, but also even in the process, if you've got 15 layers, anything that falls onto that layer between them causes all kinds of problems. How would you describe the environment in which semiconductors are produced? Clean, dirt-free. It's the cleanest places on the planet. Yep, safety first. Oh God, Dave does not think he's an artist. I think that's it. So do semiconductors have to be a certain temperatures to work? Temperature and semiconductors are a funny thing. Certain semiconductors circuits react well to heat, so they actually lower resistance. Some of them react very poorly. They drift, especially anything that's light emitting. So LiDAR has a laser. If it gets hot, the color temperature can vary greatly. If you have an LED light bulb and it gets hot, it'll actually start looking orange because it does not like heat, and actually it starts dying pretty quickly. So most of the time we build this thing I showed you earlier. This whole back is a heat sink to try to keep the semiconductors cool, because you don't want them getting so hot that they actually break down. And are there other external factors that could affect how well a semiconductor functions? Oh, absolutely. We used to call it a squawk test when I was an engineer, where you took a walkie-talkie and you went up to a board and you just clicked it. That radiated energy can change all kinds of things on a circuit, because I'm not going to get into antenna theory, but what you can do is have a little lead of metal that acts as an antenna, and all that energy goes right into your chip and blows it up. I've seen a crazy instance where somebody called me for help because they said every time the board bent a little, it changed the whole circuit. And sure enough, we found out that when you stressed one of these substrates, the gain on the amplifier changed. So it went from being an audio circuit that was a little bit of noise to a ton of noise just by pressing on it. So there are a lot of different factors: seismic, RF, radio frequency, EMI, solar, all kinds of things will impact the performance. That's also why they're put in an insulator, a big epoxy, an epoxy patch, if you will. That's why they look black. There's a big chunk of plastic on top of each of these chips to protect a lot of it. And some of them even have little copper cages to protect them from radiated energy. So yes, a lot of factors that affect the performance of the whole circuit, not just the semiconductor.
Awesome. Thank you, Dave. Wow, you had so many questions. And they were
it's a complicated subject to squish into 15 minutes, but I really appreciate everyone's time and staying with it.
Awesome. Well, thank you so much. That was absolute wonderful. I think everybody on the call today learned a lot from you. So thank you again for your time today. We really appreciate it.
No problem at all. My pleasure. Thank you.
Yeah. Well, Al, I think we'd love to turn it over to you. How does that sound to you?
Sounds fine. I'm ready.
All right. Sounds great. Go ahead and turn it over to you and take it away, and I'll have Kelly go ahead and spotlight you this time, so we have you highlighted. So go ahead and take it away, Al.
Okay, well, I actually have some things to show, so I'll wait until the board comes up, but basically we're located our global corporate headquarters. We've been recycling since the old Motorola days for over 40 years. I started working at Motorola in 1978 while I was still a student at ASU. Over the years, I've held many positions, primarily in supply chain, purchasing, etc. But when we became on Semiconductor, they really started taking the recycling more serious, and it became a bigger issue and a full-time job. And I was lucky enough to be there, to be the one that helped keep it going. So we get all the scrap from 22 different manufacturing sites, and most of it from the subcontractors we hire. We get it from the front ends, the wafer fabs, and we get it from the back ends in assembly and test. And a lot of the material we get when we say manufacturing scrap from the assembly and test sites, we get things like this. This is a lead frame, and a lead frame is like when you're building a model car when you're a kid, you pop out all the parts, only this is all done by technology. And once you get everything out of it you need, this is what's left over, the frame. And so these particular ones are aluminum. So we recycle these. They primarily just go to a plant, get melted back into aluminum. We also get tons and tons of copper. I didn't realize how much copper we used, but that's why we get a lot of it back. The majority of this material that is scrapped gets recycled. Another material is nickel. There we go. Let's get some nickel in there. It's shiny, looks pretty. But we get the material at every step from the wafers with different coatings on them that all have to be processed differently to finished products like Dave was showing. We have so many. This is an image sensor. I want to say a plug for the image sensor people. On Semiconductor just got an Academy Award for the image sensors that goes into their cameras, and they make a lot of movies and TV shows. When you see that 8K picture, it probably has a non-semiconductor image sensor. So that's pretty cool, I think. What we do is, this is a collection and sort facility. We get stuff that's already sorted from manufacturing, but we also get material from the distribution centers that either failed or went out of warranty or for whatever reason. And so we get these parts like this. And I actually have some of these little parts Dave was talking about that are about the size of a grain of pepper. And there's probably about 10,000 of them in this little container. We also have sensors that get their power from a Bluetooth signal. For instance, this particular sensor looks like a piece of paper, but if you stick it on the side of a water level meter for your windshield washer fluid, a Bluetooth signal will send a power to it, and it'll check how full it is and bring it back to the sensor and tell you that you're low on washer fluid. So the fun thing about this job is I see all the stuff Dave does, only we have to figure out how to get the material back out of it and make it reusable again. We work on the premise of a circular economy, and that's what we're shooting for. All the metals we melt get put back into the market. Right now, it's kind of a choppy market. Like when we melt gold or silver or platinum, it goes back into those markets that sell it. And then some companies purchase it and make targets out of it. And targets, it's going to get complex, and I need Dave to help me, but you put the wafers in a planetarium and they put them in a sputtering machine, and it's vacuum. It's all completely vacuumed out, and the waves hit the metal and it sputters it onto to make different layers on the wafer. So if you ever have a chance to tour a wafer fab, I know they don't like you walking through them, but you can get a window tour. It's one of the most fascinating places you could ever work in. I worked in the ZR fab for 3 years. It was as a purchasing manager, but it was the time spent in the fab that was always the most interesting. So the primary reason we started recycling, Motorola did back in the 70s, was to protect our intellectual property. Found out there's a lot of people in the world that like to steal this intellectual property. And so we have kind of a closed loop system that everything that comes out of ATO that fails and out of the distribution centers comes directly here. I have a secure warehouse with 2 layers of security to get in. And so only certain people have access to this. Last year in 2020, we received about 2 million pounds of scrap material. We shipped and processed over 1 million pounds, 1.4 million pounds actually. We have regular scrap, we call it, the warehouse material. That's copper, aluminum, nickel, tin, cardboard, plastic, all the other metals. And then we have precious metals like gold, silver, platinum, palladium that obviously are refined differently. And we actually have a third level of security for the precious metals. Last year we don't generate revenue, but what we do is offset manufacturing costs. And in 2020, even with the COVID and all the issues that were involved with that, we still managed to generate $23 million in cost offsets. So that was a very good year for us. Also, because of COVID, the prices of the metals were all high, and that's already starting to fade. So we can't ride that crest of financial value for the rest of our times. So we work with the Responsible Business Alliance. I work with all the Arizona Recycling Coalition, Arizona Forward. We work to try and have sustainability throughout our system from beginning to end. That's why we receive material in every state of manufacturing from beginning to end, and even some back from customers. I say we get 2 million pounds of scrap, and that sounds like a lot, but if you think about how many billions of units we make every year or every week, there's some units, the lowest amount you can buy is 10,000 because they're so small and the value is low. And there's also ones on the higher end of that scale as well. So basically that's what I do. I recycle all these materials. We take them to refiners. This is a printed circuit board from a hard drive. This is an old cell phone printed circuit. It's actually a BlackBerry, and you can see all the gold that was used on the keys. I don't think there's that much gold in the cell phone anymore. We get copper ribbon. We get copper pins. I don't know if you can see that very well. But all this stuff, we categorize it by lot number, and every different unit and every different piece of precious metal has a lot number. And we have about 250 lot numbers, and everything is sorted by lot number. That way, when we take it to the refiners and process it, we know exactly what we're going for, what we're trying to get out of it, and we have an expectation of how much that'll be. We use several different refiners. Some of them are better at some processes than others. And we've had 40 years to filter out the ones that aren't as consistent. And the ones we use are the world-class refiners that are still in business for the last 40 years. And we don't like to change unless we have a really good reason. This year presented a unique issue, or the past year with COVID, because all of our material, when we process it, is usually witnessed by me or one of my employees at the refiner. We send the scrap there, meet it at the dock, break the seal, and watch it get weighed in, we make sure the weights match, we make sure it's sorted properly, and then it gets processed properly through the each step, depending on what the material is. This year, a lot of refiners, because of COVID, wouldn't allow people in, and I'm not sure I wanted to get on a plane anyway. But we do have some refiners that offer virtual witnessing, and that has really helped keep us operational more than anything, is the ability to virtually rep and see what's going on with our products. Because a typical gold melt, for instance, is $2 million. So it's very important that somebody from our organization witnesses that. What is the coolest thing I have recycled, and what has it been converted to? Well, we recycle, for instance, parts like these, and you actually will pull copper, a little bit of gold, a little bit of silver possibly, a little bit of platinum. All the different lots, we get different materials from. One of the strangest items I've received to recycle is a little block of, looks like a chrome bar, but what it is, when we shoot it with our XRF gun, it's actually gold and mercury melted into a solid bar. And I think some guys at a lab were just experimenting around, and I got about 10 pounds of that. And there's only one refiner in the US that would actually recycle that, but they have a minimum of 1,000 pounds. So that 10 pounds we have floating around here is a paperweight on everybody's desk. So we have mercury and gold paperweights on our desk, but nobody would ever know it, and they would never be able to get any money out of it if they tried to sell it. I've seen lots of questions pop up. Yeah, paperweights is a cool material. So we have we generate lots of paper in this industry because we have all kinds of checks and balances to make sure. With the U.S. Patriot Act that took place in 2006, we have to pass these anti-money laundering programs, and it gets real tight because, unfortunately, I found out that scrap metal is one of the largest tools to use in money laundering. A cartel can go buy 1 million pounds of scrap in Brazil and then sell it in India, and then they have laundered money. And so we know exactly where our material goes, what happens to it afterwards, and where it goes and when it comes back into the system. And there's a big team of us right now that are working on a 5-10 year project to get the circular economy more viable for more people. And on Semiconductor, I think we're very good at the circular economy, maybe a little bit ahead of other companies. Very few companies do single focal point refining. They'll do it from each of their factories with local vendors. By bringing it all here, we first of all get better rates from the refiners because we have massive quantities, 40,000 pound lots that can go out, and we get pricing based on the volumes. And we also can better protect our intellectual property, and we can actually witness everything that gets processed, which if you do it at 22 manufacturing sites around the world, it's going to be a lot harder to do that. While we do have some local sites that recycle, it's primarily on precious metals, because a lot of the target manufacturers will take the targets back and remanufacture them and then resell them back at a discounted rate. There are some benefits to that on the lower grade targets with the gold, silver, and platinum. Primarily, those come to us. Dave was talking about the silicon, and it gets cut up. And this is a piece of silicon that was went through assembly test, and these are parts that have a black dot on them that actually failed. and they're stuck to this Mylar tape. And so when it goes through assembly test, it goes to a probe machine and it tests every circuit, every one of these little dots on here. And the dots that are no good, it just passes them on through, leaves them attached to the Mylar tape. We get them and we run them through a refining process and we get all that precious metal back. I'll tell you what, I'll give you what our reclaim objectives are at On Semiconductor. Reflect our commitment to the environmental sustainability and resource conservation while optimizing our network, protecting our intellectual property, and maximizing and recapturing the profits. So in a perfect circular economy, we would get a lot of revenue back so we could build more semiconductors. One of the things we've been doing with plastic, since China no longer accepts plastic as recycling, and I don't blame them. Plastic's difficult to recycle, and there's very few people that do it in any kind of volume, even within the US. People have told me might as well just put the plastic in the landfill because it doesn't have any value. Well, there's a company in California called Covanta, and they've been around for 20 years, and they actually turn scrap metals and plastics into electricity. And if you go to the Covanta website, you can see how they clean their stacks and make sure that no emissions are released while burning the plastic and turn it into electricity. So I have a thing about landfills, and I don't like to put anything in the landfill. I don't want anything to go to the landfill. When I was young, back in the 60s, landfills were everywhere, and a lot of places built parks on top of them, and some cities are built on top of landfills from hundreds of years ago. And I don't want to see my earth covered in scrap and garbage. Nothing breaks down in a landfill. If you put it in a landfill, it'll still be there in 10,000 years, just like you left it. So for me, I burn the plastic. That's makes me happy. And it makes me feel better that we're doing the right thing. We get precious metals in many different kinds of forms. The target form, it's a solid piece. We get flake that is peeled off of the domes from the sputtering and evaporators. We get platinum, we get nickel, tin, silver, just every kind of flake you could imagine. What advice can I give to those who want to get started today? Recycle. You can recycle at home. My wife and I have been recycling since the 70s. Everything is recyclable. Find out where in your community has a recycling processor. A lot of communities put out the blue bins. Make sure you follow their rules and only put in the recycled materials. I live in Queen Creek, and we have a recycling center where you can take your material to the recycling center yourself. And so my wife and I collect all of our recycled materials, and my wife, she rinses cans and bottles out. That's truly not necessary, but we recycle about 90% of our waste from our household, and we might have a bag of trash a week, half a bag of trash. Everything else gets recycled, and we feel very good about that. And even leftover food, waste, coffee grounds, you can compost it, use it in your garden. There's 100 different ways to recycle. So if you want to start, I actually started recycling when I was a kid. We'd pick up cans and sell them to the recycling center, aluminum cans. And going back even further, this is going to age me, but I have been doing this for a number of years. Bottles used to have, you could turn them back into the Coke bottle company, and they would give you 3 to 5 cents a bottle. So if we were short on money, we'd go around and collect bottles and bring them to the store, and we get paid for them. And not only did we get money, but we kept that material from going to a landfill. So we actually had a brownie troop in the early 80s when my daughter was about 8 years old. And we recycled cardboard, newspapers, and aluminum cans. And that was where we generated revenue for events for the brownies and Girl Scouts to do. And that was a lot of fun to get everybody and their parents involved in recycling. And it's very cool.
Very cool.
I actually like it. I find it very rewarding that I'm not adding to the landfill. And,
Al, we do have one more question for you, and then we'll go ahead and turn it over, I think, to Martin. But can you unravel the semiconductors back to its original element state? Meaning, can you separate the silicon apart from the coppers and recycle it in that way too?
well, the silicon is going to have all these layers of different metals on them. Okay, so what we will get is all the different metals off it. We don't actually, we do sell clean wafers, N-type and P-type, if they have no patterns on them. There is a small demand, nothing like there used to be. Everybody wants, they use the used wafers for test and dummy wafers. Anybody have any other questions? But yes, we bring every element back out that we put into it, except the plastic. The plastic is going to get burned off in one of the processes.
Awesome. Thank you, Al, so much for sharing all of that. And I love what On Semiconductor is doing to recycle and repurpose and reuse those precious metals and things that are coming in. And keeping them out of our landfill. So thank you so much for the work you do and for sharing that with us.
Thank you.
Awesome. All right, Martin, I'd love to turn it over to you now. Thank you for joining us today.
You are welcome. Can you guys hear me?
We can, thank you.
Okay, good. Okay, my name is Martin Clark. I work in corporate R&D here in Phoenix, Arizona. I've worked in semiconductors for just over 35 years now. I started when I was 17 years old. Motorola hired me straight out of high school, put me through an education, gave me what they called an apprenticeship back then, gave me all my training, and since then I've just fallen in love with semiconductors. Came across from Scotland in 1999, working for Motorola. I then converted to Freescale and worked through the Freescale days, and then came to On Semiconductor back in 2007. So I've been here for about 14 years now, working in the corporate research and development lab here. And specifically, I'm a staff engineer in the technology development lab. And in the technology development lab, we're responsible for coming up with ideas and concepts to make new microchips, and also the manufacturing processes that those microchips run on. So that's what our group does here. And specifically what I'm going to show you today, it's going to be an interactive tour today, where I'm going to walk you through some of the test equipment that we use to characterize and test some of the chips we make. So as you can see up here, it's a technology development lab. And inside this lab, there's millions of dollars worth of equipment. So access to the lab can only be gained through special card access to individuals, which we have on the wall here. So let me take you a walk through the lab. And we'll take you through some of the equipment we use in here. So first thing I want to show you is, I just explained our group comes up with some of the ideas and concepts of new semiconductors and the processes they run on. That starts off with a desk job, where engineers sit at their desk and do simulations of a silicon wafer and a silicon process to achieve a specific function. Then that concept is brought to a chip level basis, where we lay out what it would look like as a transistor, which is an electronic component which can act as a switch, or it can act as an amplifier. And then we take that to a manufacturing process. The manufacturing process produces wafers, which Alice just went over, which I'll show you in a minute. And those wafers are then tested in our lab. So it starts off from the concept of just an idea we have, through to the manufacturing process, through to the wafer, and all the electrical testing, characterization, and proving out the design is done here. So some of the products that we have and the design here is you guys are familiar with this. It's an Apple charger. And what On Semiconductor does is, in our group in particular, we use our chips to convert basic voltages and currents from AC, which comes out of your wall, into DC, which a cell phone or a laptop would use. So this is one of the guys we use, or we get chips in, and everything from the wall all the way through to the cell phone to the computer on his chips at every stage to convert that wall voltage from 240 volts AC down to about 1.2 or 1.5 volts DC inside a computer, and it's all done with On's chips. One of the other applications we have is for automotive. What we're looking at here is what we call a PIM. It's a power integrated module. And the back of this is a large slab of copper. This copper is used to conduct the heat away from the internal components in here. And it actually plugs into the module in the car for a braking system. You can see these little pins here where it connects to the car system. These would typically be used, this one in particular, I believe is used for Toyota Prius. And it's also used in, we also use these in various other applications as well, in various manufacturers. You can take a look inside this if we take it apart. And what we're looking at here, you can see these each individual little squares. Each one of these squares inside the module is an individual microchip that we make. And you can see within those squares, there's tiny little wires which can connect all the squares together and output them to these pins, which then goes in the module and gets plugged into the car for a braking system. So how do we go from concept to these really cool chargers and really cool modules that we have just now? What we do through the manufacturing process is we manufacture wafers, as Ali touched on. These wafers through the manufacturing process can take up to 6 months to manufacture. And they're made from silicon. Now, it's not the same silicon as you see on a silicon straw, a silicon bakeware or cookware in the kitchen. This silicon is essentially made from silica or sand, the type of sand you see on a beach. And the wafers are very, very fragile. This is the back side of the wafer, how it looks before it's manufactured. And after it goes through 6 months of processing in one of our wafer fabs, this is how it comes out. I'll just try and take it away from the light here. This is an 8-inch wafer, and On has multiple fabrication sites throughout the world manufacturing these 8-inch wafers, all the way from the US through to Europe, through to Asia. We've got manufacturing sites. And we've just started acquiring our latest manufacturing site, which was actually a 12-inch facility. So these wafers will go from 8-inch to 12 inches. Within these wafers are individual microchips, which are eventually sawn up and used to go into the applications we just saw. Okay, so let me just put this back. So whenever we get these wafers, we can through to our lab. And what our lab does here in Phoenix is we test and characterize these wafers. And they're typically done through test equipment that we have in this lab. And what we're looking at here, we call this a pizza oven because that's exactly what it looks like. The reason it's enclosed in black metal is because semiconductors are typically sensitive to light, and the light can change their properties. So when we're testing them, we want to keep them in total darkness so they're not affected by any light entering. So if we open this up, this is what it looks like inside. This is called a prober. So the test equipment we use consists of 2 major components. There's the prober, which we have here, and there's actual test equipment over here. This test equipment we're looking at provides electrical stimulus that we want to test the chips with through all these cables and wires, and right up to the wafer, which goes on here, which is called a chuck. So this chuck here, the wafer would sit on here, and it can also be heated up. Right now it's sitting at 25 degrees. We can take this as low as minus 30 degrees and all the way up to 300 degrees to test either cold or the temperature. The connections to the actual chips in the wafer is made through these guys here. This is called a manipulator. And the manipulator has various controls to move a little probe needle back, forward, up, down, in and out on here, which is so small we can hardly see it. You can just maybe try and catch a glimpse of it. Coming off here, we'll have a look at them in a second in more detail. So these little probes touch the wafer and carry electrical stimulus from the tester through the cables and onto the wafer itself. So that's one of the test systems we use here. This tends to be a modular test system, which means this all this electrical equipment is in a rack with wheels on it. And this equipment can be wheeled about to different probers. We've got various probers throughout the lab of varying degrees of complexity, and various test systems like this of various degrees of complexity. This one in particular here is an oscilloscope already attached to it. And you can see there's two waveforms, a yellow waveform and a purple waveform. This would typically be used to characterize and measure parts against an expected signal. So an expected signal would be the yellow path, and part under test with the purple path. And you can see there's a mismatch between purple and yellow. Just at the end here, that would tend to indicate a fault with the component we're testing, which would need more evaluation and more testing and some debug on it. So let's see how this goes together through next door. This is yet another part of our lab through here. And we've actually got a live setup here where we've got, again, our prober, very similar to what we looked at. We've got another tester, which this time it's all computerized. So rather than the individual components we see through back that we just looked at, this here is all computer driven. And again, it's through all this cabling. This cabling here gets connected to manipulators. And these manipulators can conduct the electrical path through the probes and onto the wafer on the chip here. If we have a look at some of these probes, these probes we're looking at just now are about probably about a tenth of the thickness of a human hair. And you can see there's a large metal part at the bottom, but you can see towards the top how fine the probes are. They're so minuscule, if you touch them, they'll just break and bend. So you can't touch these with a finger or a human hand at all. Through here, we can see there's a light that we can turn on here. You can see the dot of light appearing. And let me try and take you through the microscope just now if I can. Let's see if we can do this. So through the microscope, you can see those two black lines on the left-hand side. Those are actual probes themselves, and they're touching tiny little pads. Those pads are about 100th of the width of a human hair. And let me just try and close up in that. Let me try and zoom in a little bit closer using a microscope. So this time we've zoomed in, and you can see those probes touching the little pads. So those probes at the tip are probably about 100th of the width of a human hair. So that picks up electrical signals from the wafer through the wires into this test system here. This test system we can configure in various ways. So if we look at the measurement setup, we can go through various menus and set up what the electrical test is going to be to the probes. And then we can come across here and actually test the material. So you can see that did there. This is an actual test on the component that's over in that tester just now. It's actually a resistor, and we're doing a pulse test with various pulses through the resistor. The blue line is measuring voltage, and the orange trace that you can see below is measuring current. And on the x-axis here, we've got time, so it's 10 milliseconds each pulse, and the y-axis we've got voltage. And again, let me just run that again, just so we can see it happen in real time again. So we can close out of this and run the test again. So you can see it actually builds up. So that's a very simple test setup with only two probes that we use to check very simple components on these wafers. However, sometimes we get much more complex components which have multiple pins or pads that need to be tested because it's a much more complex device. And over here, what we use for that, rather than manipulators, we use something called a probe card. So this is a probe card here, and each one of these little white fins is actually connected to a probe below it. Let me just flip it over. You can see these tiny little wires, which are, again, about a tenth of the thickness of human hair, and they're so close together you can't even tell the difference of them apart on this probe card. Okay, this probe card typically goes over to a semi-auto prober. So we looked at the prober over here, which is a very manual setup. where we've got to take the manipulators and manually put them down and touch a wafer. These probe cards can actually fit in these types of prober here. And you can see this is a probe card already mounted in here. You can see the various probes down here, just ready to accept a wafer. This prober in itself takes a whole load of wafers that we just looked at. So if we flip up this, we can see we've got a whole cassette full of 25 wafers in here. You can see just the top of that wafer there. And it fits up to 25 wafers. And this can be left on automatic mode. If it takes one wafer at a time, it'll take it under the probes. It'll probe about each chip on the wafer. It'll return the wafer to the cassette and take the next one. In the meantime, storing all the test data in files that engineers can read. So that's an example of a manual prober and an automatic prober we use here. Through the lab, there's lots more equipment through here. Some of these testers we're looking at today is in excess of $1.2, $1.5 million for these types of testers here. This is called a Keithley 530, and this tends to be for automatic testing. So rather than a manual intervention we just looked at, this would be set up purely by the engineer at their desk by talking to the tester down here, and then they set up their wafers as we just looked at. They set up wafers over here. See the wafer sitting in there, and this would run all day, just feeding information to the engineer back at his desk. So that's one of the automatic test systems we've got. We've got another test system over here. Again, this is another type of prober. And you can see up here, you can actually program this prober with the individual chips on the wafer. So this is looking at a simulation of the wafer that's on the chuck. And you can see it divides a wafer into individual chips that's going to go and test. So we can pick and choose which ones we test and which ones we don't test to make the whole test time quicker. Again, this is a prober with the wafer would be inside it. And the test system is very similar to the one we just looked at. It's all computer driven. Again, coming over here is yet another type of equipment we use. And we can see again, this is covered up so no light can get into it. We can see there's various black covers over it, just to make it totally oblivious to any kind of light patterns there may be. And again, a computer driven tester next to it to keep all the signals in. This guy over here is another full automatic prober. And we can actually take a look at the complexity of some of the wiring we have. We can look behind us at a sneak peek at just how complex it is. So you can see the amount of wires and test channels come out of it. And looking into the back, it just looks a whole big bowl of black spaghetti. You can take all the signals for testing. Some of the circuits we test here, the actual kind of microchips that we test, the feature size of some of the metal lines for the interconnect and for the wires inside it are 1,000th of the width of a human hair. That's how small they are. And this test system here also tests at very high speed. This can test 1,000 millionth of a second. Various signals get into it, and it's what they call a transmission line pulsing system. It tests very quickly, so the semiconductor doesn't get a chance to heat up because properties change when microchips heat up, and we don't want that. So it can test very fast with very fast signals to avoid any heating of the chip. Last thing I wanted to show you is one of the cool things we have in this lab. We were spending lots of money on getting test fixtures made up from local manufacturers and local shops around the valley. So what we did is we went and bought ourselves a 3D printer. And those manipulators that I showed you before, which were sitting in test systems, those typically cost $1,000, $1,500 each. And we've got tens of those manipulators we use in the lab. So it's very, very expensive. What we can do with this is we can actually make our own manipulator. This was a 3D printed manipulator that we made here in the lab at a cost of about $15 to $20 in comparison to $1,000 to $1,500 for the ones we buy off vendors. So that's a big cost saving we make in a lab. The lab's quiet just now because it's so late in the day and because of COVID, we're restricted to how many people can be in the lab. So we're lucky today we actually got to tour around it without anybody being here or without disturbing anybody. But that's basically the lab and what we do in the technology development group within corporate R&D on Semi. Like I say, I'm Martin Clark. I'll be happy to take any questions you guys have.
Martin, that was wonderful. Thank you so
Thank you.
much. That was so cool to be able to go through and see the, the behind the scenes look at at that lab. That was definitely awesome. We had a couple of questions for
Sure.
you. So that's a lot of machinery and technology. What kind of training does it take to run, to work in that sort of lab and do that kind of work?
We range from technicians, which are college graduates, up to doctors. We get a lot of PhDs in the group itself. But to actually come down here and be competent to use all the equipment, it takes probably a year to 18 months just to get comfortable with equipment, and probably 2 to 5 years to become proficient at using it. So it's very complex and very complicated. Upfront training, people to use a lab, but when people get comfortable, they can do lots of kind of really serious work in a very short time, which really benefits us down here.
Awesome. Yeah, I would imagine it would take quite a bit of time. It looked very technical for sure. So, I think I'm trying to think if Dave talked about this before, but do you produce any Wheatstone bridge sensors? If so, what is your production rate?
We don't produce sensors Wheatstone bridge sensors per se, but we do manufacture the components that goes into them. So Wheatstone bridge sensor or a Wheatstone bridge or other various kind of conversion components will use individual transistors, and we manufacture and design and test the transistors that goes into those systems. So we don't have a final system per se, it's the components that goes into those systems that we design.
Great, thank you for that. And then early on, you grabbed, I think, the wafer with something. What did you grab it with?
That's a great question. What this is a vacuum wand we're looking at just now. Let me just flip the camera around again. So this guy here, you can see it's got a curly lead, and it plugs into the vacuum, house vacuum. It's got a flat tip on it, and the hole you see here is a vacuum which is actuated by a button. So this button switches the vacuum on and off, and the way it's used is, let me just go back to the wafer. So you can put it on the back of the wafer, and you just feel it grabs suction on it, and you can pick up the wafer. What I'll do is, you can see if I press the button, if I pick the wafer up and press the button, right away it just disengages. So that's how we handle the wafers. The wafers are so sensitive that we can't touch them with bare hands because it will contaminate them. So they've always got to be handled with a vacuum wand. Not even gloves are sensitive enough to handle these wafers without them getting impurities and affecting the performance of them.
That makes perfect sense. That was a cool tool. That was really awesome. But yeah, it makes sense that you can't pick it up with your hands for sure. Yeah. So one other question. What is the coolest part of your job?
The coolest part of my job is seeing what we do at our desks in advance, waiting 6 months for the manufacturing process, seeing the wafers come out, test the wafer successfully, and then probably 2 years later, seeing vehicles on the road or the latest iPhone with the latest charger, knowing that our components are in those parts or in those cars. That's the coolest thing.
Wow, that's a lot of patience.
Yes, it is.
Which I think is good for our CSOs to have, and anybody else online, right? That it doesn't, some of these technologies just don't happen overnight, right? They take months and years even to get to the place that where they're going to be implemented, and taking that time is important.
Yeah. Typically from concept, when we sit around a desk and think up these ideas until we get the first wafer to test, that's typically anywhere between 2 to 5 years. It's a long process to do that.
Wow. Yeah, definitely. Let's see. Is it hard for you to work towards a goal that can't be actualized for so long? So CSO Marissa was kind of going to ask this question. You talked a little bit about it, but I don't know if you want to expand upon that or not. Do you want to read it again?
Yes, please.
Yeah, so is it hard for you to work towards a goal that can't be actualized for so long?
It's not really, because there's so much involved from the concept through to the final manufacturing process. It keeps us so busy, and there's always something to do. There's always a common theme of focus through the whole thing. So very seldom do people work in a program who halfway through it say, you know what, I'm bored, or I quit. Or the people we have in our group just now, I've been working with these guys since I've been here, and that's been about 14 years. So our group is kept together And like I said, there's just so much going on in the group that people want to stay here. You know, very few people leave or get bored because there's always so much to do.
And it sounds like it's meaningful work too. So
Yeah.
that also helps, right?
Yep.
Wonderful. Well, any other questions in the chat? Give everybody just one more second here while we look. Okay, here we go. What is one of the most important life skills, or what is one of the most important life skills to have, in your opinion?
Life skills.
Yeah.
I would say it's got to be patience, as you said. You know, like the patience is always rewarded, but there's times through the development process where we come up against disappointment, where things just don't work, or we come across problems which are hard, and they're never insurmountable problems, but they're hard to resolve. So one of the biggest life skills in this job is perseverance, knowing that there's always a solution to every problem. There's no problem that's ever beat us here. There just isn't. We'll always find a solution to every problem. And that works out with work as well. Taking that back home to the family and the lifestyle, and just persevering, even when you're at the lowest point, and think nothing's working. You know, for various aspects of life, there's always a solution. How much I've learned.
Yeah, I love that. I love that. Persistence, right, as well, is
persistence.
important.
Yeah.
So to kind of go along that same line, what advice would you give your 14-year-old self? We have a lot of CSOs, a lot of students on the call with us today. So what advice would you give your 14-year-old self?
I've got a 14-year-old daughter. I've got 4 kids between 14 and 28 years old. My 14-year-old daughter, since she's been 4 years old, she's wanted to be a vet. And every single day I tell her at school, you know, she comes home, she gets good grades, or sometimes she doesn't do so well. And I keep telling her, back to the same tone as I just mentioned, perseverance, don't ever give up your dream, stick with it, and you'll get there eventually.
Yeah, I love it. Goes back to that patience, persistence, resilience, right?
Yep.
Yeah,
Yep.
Find what you love and keep going no matter what people say.
Yeah, be driven by your passion.
What was that?
Be driven by your passion.
Yes, I love that. Excellent. Have you ever traveled to other ON Semiconductor locations? If so, which ones?
Yeah, within the US, I've traveled to New York. I've traveled to Oregon. I've traveled to Idaho. We've got facilities in all those places. And in Europe, I've traveled to Slovakia, Piastany, which is over there, the Czech Republic. I've traveled to as well. We've got a facility there. And where else? I think that's been it. So basically, US and Europe. I've never traveled to Asia yet.
Oh yeah, Kelly and I have been able to go to several different places ourselves. It's one of the things we had, I think it was Tip Thursday last week, and we were telling the students about getting their passports and traveling and, you know, exploring different cultures and learning from other people. So I love that you've been able to go to so many places.
Yeah, it's fantastic.
Wonderful. Well, let me just double check one more time that we don't have any additional questions. All right, so with that, I think we have Jeremy on the call. Maybe he'd like to say a few words as we close out and just thank ON Semiconductor for all your time today. We really, truly appreciate it. Martin, that was awesome being able to see the tour. So thank you so much for your time.
You're welcome. I enjoyed it. Thank you.
What we're hoping to do is really start to build a data bank of all these different opportunities in advanced manufacturing in companies like ON. And, you know, this is one of the first that really hits the mark at that level. And I think this is going to set the standard for how we're hoping other companies will also do this sort of thing. So we really appreciate, we know it takes a lot of time. We've had other in-person tours at ON. And so it's pretty unique to have this in a virtual setting, but really appreciate the team taking a risk to make this happen. And, you know, Jackie and Nihal and the other members of the ON team to do so. Thank you for making that happen.
Awesome. Thank you, Jeremy. And so I think with that, again, thank you ON Semiconductor for your time today. We really truly appreciate everybody being on, sharing your expertise with us. Appreciate Gail and all the work, you know, and Jackie did and Nihal did to set this up, Chris and Dave, and we had Al. And we had Martin all joining us. So thank you so much for your time. We really, truly appreciate it. And I know our CSOs really liked it as well. We did video this and it's been live on YouTube. So we'll be able to reshare it again over and over again.
This is great. Thank you so much for inviting us to be a part of this. You know, having been an employee at ON for, I think, about 6 years now, some of this was new information for me as well. There's always just so much to learn. You know, I think our entire operation is so complex. So thank you again for inviting us. And thank you to all the ON Semiconductor presenters today.
Yeah, I've been with the company going on 8 years in March, and every year I learn something new, even with Al or Alexander Falk. He does our reclaim center. I took that tour the first year I was part of the company, and every year it's something new. So
yeah, it's wonderful. Well, thank you all again. Truly appreciate it. Oh, it looks like Al might actually maybe be finally leaving work since he went at like 4:30 this morning. So
yeah, he's
gonna
got a long day.
go home and get a snack, hopefully, Al. Appreciate all your hard work.